Uh, so I'm going to start with the slide that I presented in the morning. So I'd like to say this, that in this course, please feel free to ask questions and basically keep on interrupting me so that we also have, so anything that you think is not clear, so I can quickly go over that. So that way we keep it interactive. So otherwise I'll be just lecturing and you'll be listening. So it's good to, like the Vice Chancellor said, let's ask questions so that we can both be on the same page. So graph analytics is, of course, a very important topic, right? So as I mentioned in the morning, we're obviously living in this interconnected world, right? So social networks are one of the big applications for this kind of technique. So you have the Facebook social network, or the Twitter, retweet network. You have LinkedIn, for professionals. So all those sort of large-scale networks. One of the key things is, what can we do? What can we understand? What are the dynamics? How do these tweets spread? So that's a whole set of questions one can ask. And the most promising research there is sort of, in conjunction with computer science and social sciences, to basically try to understand the social phenomena. But then, of course, you can look at, things like protein interaction networks, right? So these are, in bioinformatics, in the life sciences, you can measure how much of a protein is present in any given cell and at any given time. And then you can start making these networks, right? So these two proteins, they are present together, they are located at the same place, they interact with each other. So you build these huge, protein interaction networks. You can build gene networks. Again, the whole point is that what can we learn from these interactions, these complex biochemical processes, because that's what we want to do to understand disease, to learn the basic biology. There are other, you can talk about transportation networks. This is more of a human design network as opposed to a naturally occurring network. But again, what are the properties of such networks? The World Wide Web, again, the physical layer itself is a network, right? Routers and hubs and all that. But then the actual information is the web pages and how they're interconnected to each other, the portal side. And now we are in this era of knowledge, information networks. So here's the example of, where you have lots of semantic data, right? So the idea is that, if you look at the present day, a company like Google that provides a great search engine, right? It's still very primitive, right? Because when you want to search for some information, you have to, give a bunch of keywords. And that's a very, very simple way of asking things, but it's not, the idea is that can you go beyond that, right? So you want to do question answering. You can say, for example, who's the president of India, who was the president of India between, the first president of India, for example. So those kinds of questions you cannot ask Google today. However, right, under the hood, they're building this whole infrastructure called the Google knowledge graph, and you can now ask the Google Voice Assistant, or Microsoft has its own agent called Cortana. Apple has Siri. Right? So we are slowly and shortly going towards that, where you can ask these queries in a much more natural interface that human beings can ask these things very easily. But then behind that, you have to have this huge network of interconnected entities, right? So you need to know that this person is a president, India is a country, and countries have presidents and they have terms. So there's a lot of sort of semantic knowledge that has to be built in. And so many of these, there's a lot of what I call linked open data, and there are these knowledge bases like the Freebase and Yago and DBpedia, and you can, there's a sort of the Wikipedia can also be converted into a semantic format. So again, there are many data sets with lots of connections, and the real value is if you can really leverage that, those connections to understand, to answer a simple query. But we want to go beyond query, right? So querying is fine because you have the question you want to ask in your head, right? So you're saying, okay, find me. It's more like fact finding, right? So it's like a personal assistant who can tell you at any given point in time, something that you want to know. But what the real value is, if you can actually extract hidden patterns, if you can actually think, things that are not obvious. Because that's where the real value is. That you did not even think of asking that question, and this is able to connect facts and things, and basically be able to say, oh, if you look at the whole picture, this is some new thing we found, and this is actually extremely important to do in the sciences. If you want to understand the basic biology, like I said, in the social sphere, right? How do people interact? How do ideas spread? Right? Viral marketing and how these cascades happen. So all those questions are extremely important, and they're all within this realm of graph analysis. So if you look at these networks, you have so there are really two aspects when we talk about graph analytics and graph mining. One should think of the two things. One is the structure, right? So there is a topology. So so this is ignoring all the information really. It's just saying that these two nodes are connected to each other, right? And that's all we need to know. And so I have maybe a network with, if I look at let's say a Facebook network, each person is a node in that network, and you have your friends, that would be a friendship edge, for example. But we'll ignore the actual semantic meaning of an edge. We'll just say you are connected to someone else, they are connected to someone else. So you have this huge network of 1 billion people with, 10 or 100 billion edges between them. So that's just the pure structure part, right? So what can we learn from this purely structural point of view? Right, so in fact, today's lecture will be purely on that structural part. But what we have to also realize is that beyond the structure, there is actually a lot of rich information, right? So there are nodes have labels, nodes have attributes. They have text, for example, if I'm talking about text documents or hypertext, where the web pages link to each other. So how do you actually use the content? So I'm using the content or the attributes or the features of the nodes in this mining process. What about the relationship? So if you have two nodes, they're interconnected with each other. So let's say in a Facebook, it would be, okay, you are someone's friend, so there's a friendship edge. Okay, someone else, you have a connection with them because they are family, so that would be the label of that edge. And you can have multiple such labels on the edges also, right? So there are different relationships. So this is what I called a rich, attributed, or an enriched network. So they're all interchangeable. Attributed, content. So that's the other side. And the key challenge is really how to link these two together. So there is a structure, then there is this content, and the content can be dynamic, right? So, and in fact, the structure can also be dynamic. So things can change in time, right? So if you look at the Twitter, retweet network or followee networks, obviously there's a whole lot of dynamic going on there. People are retweeting things as events are unfolding, perhaps. And so one can obviously talk about the temporal aspects, right? And so that's one of the cutting edge, research areas, is to understand the temporal dynamics of these networks, the connections themselves, but also the content, how the content is changing. So that's my the opening motivation that we need to look at these networks from the point of view of the structure, the topology, and the attributes or the labels on the nodes and the edges. And so first we can say what are the kinds of questions we can ask. So looking for hidden patterns, looking for basic structural properties. So today we will focus mainly on the graph mining, or the graph analysis from a structural point of view. And then later on, like in the next lecture, we'll talk about pattern mining and those kinds of things. So let me start with very simple, introduction to some of the concepts, and then we'll look at the structural properties first. When are we supposed to wrap up or
1 hour?
break? These are lecture slides from my book. So I'll be using those, but I'll be annotating, so doing things on the slide. we'll be looking at the structural properties, right? So I'm going to define some concepts which are maybe quite familiar to you, but we'll just make sure that everyone is on the same footing. So we want to look at a graph, a large graph, possibly with billions of nodes and edges. And we are only interested at this point in the structure itself, that is the nodes and the edges. So what are the things we can do with that kind of a structural information? So there's a whole area called network science, that essentially tries to understand these networks. And the motivation there is, to give you sort of a preview. So if you look at the history, about in the 90s, in the late 90s, there's this very famous physicist called Barabasi, right? He sort of popularized this trend. So let's go back a little bit further. So in the 60s, there was a very active area of research in mathematics called random graphs. Okay, so they were basically looking at, so this is a part of discrete mathematics, right? So graph structures. So they were looking at random graphs. That is, you pick one graph out of all the possible graphs in that space and study the properties, right? So if I just go to extract one random graph, so think of, supposing I said, okay, I want a graph with 1 million nodes and 10 million edges, right? So you just give some numbers. And now you want to say, if I were to just extract one random instance of this space of possible graphs, what would be the properties, right? And so there were a lot of research effort into this, and some interesting properties came about that. For example, random networks are extremely sparse, right? Because especially we're talking about the edge connection density. So normally if you look at real world data, right, there is a sort of an information limit anyways. Like every person can be connected to only maybe 100 or 1,000 people at most. And beyond that, those connections are meaningless because you really cannot interact with more than 1,000 people. So those are sort of physical constraints to any human being's information capacity, right? You cannot really have 1,000 friends. Even if you do have 1,000 friends, maybe you really have a select few of those with whom you really interact on a regular basis, right? So there is that natural sort of limitation. Same thing happens if you go to, Flipkart or Amazon or whatever and buy things, right? There are only certain number of things you can buy. So, these online companies obviously have hundreds of thousands of items that they keep in stock. But any given person is buying only a few of these items at any given point in time, right? So if you look at that connection of who's buying what, and you try to build a graph from that, again, it will be a very sparse graph. That is, every node will be connected to the degree. The degree cannot be on the order of, so if n is the number of nodes, right, the degree of any vertex cannot be O of n, right? So it cannot be on the order of n. It has to be much smaller, maybe logarithmic in n, or maybe even smaller, some constant, right? So you're talking about very large but very sparse kind of graphs. And so these random graphs really have, if you look at the structure, they are completely disconnected, right? Because if you just put random edges, what kind of structure do you hope to see, right? So nevertheless, they studied all these properties. But then this guy that I mentioned, Barabasi being one of the examples, but many other people have looked at it in the past. Social scientists looked at it. Even in chemistry, people looked at graphs for chemical compounds and things. But let's say Barabasi, we'll give him the sort of the make him the poster child. So he looked at these real world networks, from transportation networks to the web to cell phone call graphs and so on. And then what we find is that these real world networks are very different from the random graphs, right? So there are certain properties that emerge in terms of, let's say, so for example, if you look at the degree distribution, so that's one of the key things that we'll look at today is that, so you want to understand what's happening in a real world graph, right? And so if you look at the degree distribution, which is, if you look at all the nodes and you sort of arrange the degree in it, let's say from the lowest to the highest, what is the probability of finding a node with a particular degree? If you look at that distribution, there's a very remarkable difference between a random graph and a real world network. Real world networks have something called the power law behavior. Power law is a term that basically we use to describe, it's an extremely skewed kind of a distribution. It's also called like a Zipf-ian distribution. So you have many, many nodes, that have very little, very small degrees, which is what you expect in a social network, right? So you have one person, they connected to maybe 5 or 1 or 10 other people, but then you have some vertices that are extremely, extremely large. You can have millions of connections. So in a social network, this would be maybe some popular person, some TV personality or a movie star or someone or a tennis player. They have obviously lots of followers, and so they have huge degrees. But there are very few of these hub nodes. So again, there's a big contrast, right? So the idea is that what else can we find out about these real world networks? And so the study of structural properties is really to understand what's behind the differences that we observe from the random versus the real world network. So first we'll define some things in terms of what are the basic concepts. So obviously this is just, as I said, basic definitions, right? So a graph is a set of a set of vertices, a set of edges, right? So edges are connections between them. Okay, that's all clear. We can have weighted graphs. So if you want to look at the strength of the interaction, we can put weights on the edges. Obviously, graphs can be directed or undirected, right? So these are all basic things we can do. And then later on, we'll also talk about subgraphs and things, but right now we're interested in looking at the entire graph and looking at the edges between them, which can possibly be weighted. And also they'll also have direction. All right, so again, we want to basically look at the structure and look at some properties. So let's define a few more things. So first, this is the first basic thing that we'll be interested in studying later on. So what is the degree distribution of a graph? Right? So the degree distribution is basically what you do is you first find out how many vertices there are, how many nodes there are of a particular degree. So you have basically n0 is the number of nodes with degree 0. Okay, n1 would be the number of nodes with degree 1. So obviously, if a node has degree 0, means that node is isolated. It's not connected to anyone else. So not a very interesting kind of a node, right? Likewise, the degree 1 node is more like, you're hanging on to some other person, more like in maybe a star-like shape, right? So you have one. So think of it this way. So if I have one central person, and there are people connected to that one. So obviously this guy has degree 4, but these guys all have degree 1, right? So degree 1 I saw is of course very low connectivity information. So but in this graph, you'll have, first you find out how many nodes there are of a particular degree, and then you look at the total number of nodes in the network, and you can then come up with this probability, right? So what we really want to know is that what is the, so of course, this is a very toy graph, so we don't have much information, but let's say if I were to ask, okay, I have this, as an example, Facebook network, right? So what is the average degree, right? So one would probably want to know how many average connections someone has. You probably want to know many other things. You want to know the minimum, the maximum, you want to know the spread, the variance, for example, right? So those kinds of questions are obviously what we want to know from a statistical point of view. That what are the statistics of my input graph? So this is one of the key sort of distributions. So we'll say that the probability, so k here is the degree. Okay, so this is the degree. And so what we want to know is, what is the probability? So x, think of it as a random variable, right, which would stand for the degree of a node. So the degree can be 0, 1, 2, 3, 4, and up to n, right? So you can be connected to everyone else. So the size, or technically speaking, the order of the graph, which is the number of nodes, is the maximum degree you can have. So you can go from 0 all the way to n, where n is the number of nodes in your network. So that's a discrete variable, right? So this x is a discrete variable because it takes on the discrete value, right? 0, 1, 2, 3, 4. You can't have a degree 0.5, at least not yet. We'll talk about a more general notion of degree soon, So what you want to know is what is the probability that a node has degree k. If k is some constant, let's say 5 or 10 or whatever. So this is simply the number of nodes, right? The number of nodes with that. So you can actually estimate this from the graph. Right? So given a graph, it's easy to compute this number. Just count how many vertices of each k value that you have, and divide that by n. N is the number of nodes in the network. So this is the number of nodes. All right. So this is easy to compute. Now I'd like to sort of make one distinction here. Normally, when we talk about graph analytics, right? So if you're really from a statistical point of view, any network that we observe is really one instance from a possible scenario, meaning it's one sample point that you have, right? So it's actually just a single sample. And this kind of distinction is actually important to keep in mind, although we will not pay too much attention to that right now. You know, you could say that the Facebook network we see today is the universe. Okay, that's essentially an object worthy of study on its own. Or you could say that actually there could have been many, many other possible Facebook networks, and what we observe today is just one sample, okay, taken from this space of possible, networks that we could have observed. Okay, and that's really what the real perspective should be. That what we see is just one instance. It's not a closed world scenario, right? So we want to do an open world. That is, there are many other possible worlds, and what we observe is just one of those possibilities. So we have one data point really. It's a very large data point, okay, one sample. So everything that we're doing, we are trying to estimate from that one sample. But of course, we have the advantage that it has many, many vertices, many, many edges, so we can still learn something meaningful about the real world. But it's nevertheless a stochastic process. I mean, the graph could have been totally different. But that's not the point. We want to study the properties of the network in general, regardless of the number of instances that we could have had. But what we observe is just one. So this is, technically speaking, we use the hat on top of the F, right? Where the hat denotes it's an estimate. So it's not the ground truth, right? Really, it's not the ground truth, because I've not really observed all possible Facebook, connection, or for, let's say, in biology. If there's a gene interaction network, what you observe is simply, again, one sample. If I look at the human genome and the network of the genetic network, it might be different. If I look at mice and worms and other things, it might be different. So you might want to know what happens across different species, right? So again, what we want to say is that this is really an estimate. So what we're observing is the estimated degree distribution. So as I said, for the time being, we can assume that, okay, this is a graph and I just want to study it, but keep in mind that we are really only giving you some estimates of the possible. Okay, so you can now get the degree distribution, like in this, in this small example. It's basically, you simply count, like I said. So the degree sequence is, you look at this network. And you say, okay, how many, this is actually in reverse order. So this is from the highest degree, which is 4 in this case. Like, for example, V4 has degree 4. It has 4 neighbors. And the other, like V1, V5, right. So there are 4 of them that have degree 4. So, there's one with degree 3, some with degree 2. And V6 is the only one that has degree 1, right? Okay, so the degree frequency distribution, this is just the number of nodes with a particular degree. So first is n0, right? There is no node that is isolated, so you have 0 count for that. Okay, n1, how many nodes of degree 1? 1, right? So you have 1 there. How many of degree 2? 3, and so on. Right? So that's your degree counts, and then you just take those degree counts and you divide by 8, I guess, and so that gives you the degree distribution, right? So that's the complete estimate in this case, but that's, for this graph, that's the degree probability distribution. So I can say what are the likelihood of seeing a node of a given degree. So as I said, we are going through these because we're going to be studying this in the context of a random network versus a real world network. And the degree distribution is one of those fundamental, analytics that one can do just to understand what's happening in the network. Okay, so we have that. So let's move on beyond degree. So this is where the real power of the graph structure comes in, right? So the degree is something which is what we call egocentric, right? So it's just from the perspective of a single node, right? So I just say, okay, V7, what's your degree? Okay, it's 2. But in a graph, you can do much more, right? You can actually look at the connections between, who your neighbors are and who their neighbors are, right? One can actually talk about distances, right? So I can talk about shortest paths. So I can say, and this is very important in transportation networks, for example, right? That how long does it take you, like in Delhi, for example, if I'm coming from the airport to Jamia, right? How many interchanges do I have? What are the average delays on that? So if you want to do traffic planning, obviously you can model that as a transportation network. And then you'd be interested in, okay, the number of hops. But of course, in Delhi, for example, you'll have to put a weight here saying, what is the typical delay? Maybe during rush hour. So there might be just one hop, but it might be like a bottleneck, right? So this might be one hop that takes an hour for you to get through, whereas there might be one hop here, but that takes you only 1 minute to get through, right? Because you can just zip through on the highway or whatever. So in a real world, of course, there'll be weights and other things, but for the time being, we can just say, we can measure, of course, shortest paths and things like that. So that's our next, notion. So here are some terminology, just so that we are talking on about the same thing. So we hear a lot about random walks. Okay, so one of the, and we'll see that this notion of a random walk is extremely powerful. If you take any real world network and you simply blindly start walking, right? So jump from one node to the next node to the next node, but you walk with some probability. Okay, we'll talk about that later. If you can leverage that idea to become a billionaire, right? And the example is that of the PageRank, the Google's PageRank, which essentially is a random surfer model. All they did was they realized the key, component of that was that you can, if you model this sort of people browsing pages as sort of a random walk. Okay, so people go from one web page, you see a bunch of links, you like something, you jump to that one. Now you start browsing that page, and then you like something and you browse something. Same thing can be applied to the social search or Amazon or any of these other. So this notion of a random walk is an extremely important one because it gives you notions of importance. You will see one of the key things we'll be interested in knowing is which are the important nodes, right? In any given network, you want to know who the key players are. So if you have a network of professors and departments and so on in Jamia, right? And supposing I don't label anyone, right? So I don't say who's who. I just say here's the person, and here are the connections to someone else, right? And here are the connections to someone else. Guess who will show up as number one? It will probably be the vice chancellor, right? Because he's connected. A lot of people are going to be connected to the vice chancellor and so on. So the idea is that if I don't give you any information at all, right, can you infer? So in other words, all you know is that this person is connected to this person, that person is connected to that person. You only have the structure, but the key question you want to know is who are the key players, right? So that importance, again, the random walk is one example of, as we'll see, that it helps you understand which are the key players. It also helps in understanding because this randomness is a very great idea because it ties to this notion of what is called as a Markov chain, okay, which is basically one step forward, right? So you say, I'm at one node or one state at the current time, and I'll be at a different state at a different time. And the Markov property says that I don't have to remember all the history. I just need to know where you were previously, and I just need to know where I need to go next. So this only one step, is your memory. So you just have a limited amount of memory, which is a one-step, model, and that's called the Markov, property. If you want to remember the past, okay, obviously things are going to get more complicated because the question is how much in the past you have to look. And sometimes it is important to look at the past. For example, in given today's world affairs, I think more, if you look at the mass media today, it acts like it's a Markov, like a Markov network, because they forget what happened in the past, the history is forgotten. It's just like, okay, this happened today, and that happened tomorrow, and as if there was no history before that, right? So that would be a wrong assumption in the media, in politics, right? Politics is never a Markovian process, because the history does matter, right? But for many other things, it's better to just say, I need to forget what happened in the past. Okay, I'm here now, I need to go forward. That's the Markov property. So that's the property of the random walk. So yeah, what is a walk? So a walk is essentially, as I said, you hop from one vertex to another vertex to another vertex. So that's all there is. So you have a sequence, you start somewhere, and you have t steps, and you end up somewhere, right? So go from x to y, or v naught through v. I don't know why my laptop is power consumption. I think the power code is not. So that's a walk, right? The walk is essentially a sequence of vertices starting at x and ending at y. Now, a walk has no sort of notion of, you can visit the same vertex many times because it's just a random walk. So I can go from v0 to v1, come back to v0 if I want, go somewhere else, right? But a path is when the walk has distinct vertices, right? So when you talk about shortest paths, you don't talk about shortest walks, because by definition it will be meaningless to talk about a shortest walk. It has to be a shortest path. Every node should be visited only once, and you want to go from x to y, so that would be a path. So normally we talk about paths, but when you talk about random, sort of traversal of graphs and networks, we'll be talking about walks, because really there's no, you can come back to the same vertex again. So both walks and paths are important. Paths actually define, so a shortest path actually is the basic notion of distance in a network, right? And the distance is measured in the number of hops, how many edges it takes you to get from one point to the other. So that's what we'll be looking at. So the notion of distance is tied to the notion of shortest path. It's also called the geodesic distance between any two. So you can take any complex object and you can actually define a notion of distance between them. The shortest path is always the geodesic. So in our natural world, it's the Euclidean distance, right? The straight line distance. In a city, you cannot go through maybe the building and so on. So that would be more like you might have heard of the Manhattan distance, which is the city block distance, right? So you have to go through the avenues and the street, the cross streets to get from point A to point B. So the notion of distance can change depending on the application, but every time you'll be interested normally in the shortest, way of getting from point A to point B, whether it's a straight line, like if you have an aircraft, you can go to straight line, or city block, or in the case of graph, it would be the number of hops. Okay, so all right, I think the rest of the things we can talk about them when we get there. All right, so now I want to talk about one. So this is our first encounter with a matrix. So you see, networks, graphs, and linear algebra, which is matrices, and there's Markov chains and so on, they're extremely tightly connected to each other. So these are sort of the fundamental building blocks, if you will. So you have a discrete structure, which is a graph, right? All the nodes and the connections between them. But this is where you take that network and you think of it as a matrix, right? And one of the key matrices, of course, and very easy to understand, of course, is the adjacency matrix. So that's our connection to linear algebra. And I'll talk more about this as we go along. So here, basically, we say you have a graph, right? You have a bunch of vertices, and all you have to do is, for any two vertices, or any two nodes, I and j, you put a 1 if they're connected, and a 0 if they're not connected, right? Directly. So we're just measuring how many, what are the edges between the two nodes. So this matrix will be symmetric if the graph is undirected, right? So I is connected to j, j is connected to I, obviously. There's just a single node between them. So that would be, if you just have two nodes, I and j, then the entry, ij and the ji entry is the same, because they're both connected to each other. So that leads to a symmetric matrix. But on the other hand, if your graph is undirected, if your graph is directed, there's obviously an edge. So I and j. So you can say that there is a connection going from I to j, but there is no connection from j to I, right? So this is important when you talk about directed network and you can only go one way. So this would be, for example, if you have a map, right, and you have one-way streets, and you want to do a route planning, right? So obviously you have to look at the direction into account, and it may not be the same way you go, may not be the same way you come back, right? So that's our adjacency matrix. And now we come to a very interesting concept, which is that if your graph is weighted, so supposing there is a weight on this, right? So let's say a weight of 10, right? So what we do is we actually put that weight on that edge. We put that as part of the adjacency matrix. We say that instead of just putting a 1 or a 0, which is a binary matrix, we're going to put a weight. So the weight ij is actually the strength of that connection, right? And again, this will be symmetric if the graph is undirected, and it will be asymmetric, and it will be different. Ij, ji will be different if they are directed, right? Now, why am I talking about weighted matrices? Because now I'm going to generalize the notion of degree to, I'm going to skip this for a minute. So this is our first, actually I'm going to get there, so it's okay, let me backtrack. So one thing is, how do you get graphs? So that's one of the key questions. So for some applications, the graph is given to you, right? So if we talk about, as I said, the social network, right? If it's a retweet network or a follower-followee relationship, that graph is evident, right? So you basically what you extract is a graph. But many other data sets, you can actually look at any data set for that matter, and you can create this correlation graph, right? So that's the least you can do is that even if your data is, just a bunch of, points, some objects for which you measure a bunch of features, you can actually take those, you can just take two objects and say how similar are they, okay? And if you can compute a similarity between two things, you basically have a complete graph. Because for every ij, I can compute how similar is xi to xj. So here I'm using xi and xj to say x is any object, okay? Xi is some object, xj is some object. It could be me and Professor Abulaish, for example. So we are two people, and the question is, what is the similarity between us, right? And if I can compute that using whatever means, then I can use that to create a graph structure. So that you don't actually have to start with a graph to begin with. You can start with any set of objects, simple objects, complex objects, or just transactions and records and whatever, and you can compute similarity between them. And then if you want, you can threshold that similarity. You can say that if the similarity is below some value, I'm going to put a 0. If you're above, I'm going to keep that, right? So I can build a network from that. And this, by the way, it looks very simple, but there's a very, very powerful mathematics behind this. That if you can compute a similarity, and the similarity function satisfies some constraints, you get this huge power, which I'll mention later when I talk about spectral clustering and things. This matrix, if I can backtrack here, this matrix, the weighted adjacency matrix, if you can compute the similarity between 2 points, this adjacency matrix is called the kernel matrix. Okay, so let me just write it down here. So we normally use a symbol K for that. So the kernel matrix, and this is a very, very remarkable, mathematical sort of, concept, where you can say, so you can use this for non-linear analysis. You can use this, kernel matrix. So it sort of depends on what your notion of similarity is. Okay? So if you can compute a non-linear similarity, you come up with this non-linear matrix, and you can actually now extract non-linear relationships. You see, a lot of the statistics is about linear relationships. Is there a straight line, right? So you've obviously seen regression, right? So in regression, you have a bunch of points. It could be, some axis, maybe age and height, for example. right? So as, of course, as people, as children grow up, their height will go up, right? And then, it probably goes up to a point and then maybe stabilizes and so on, right? So nevertheless, you can compute the, we talk about the best fitting line, right? So the regression line. But that's a linear object, right? It's a line. If you want to do non-linear stuff, if you want to, for example, if I give you data like this, and I say, okay, here are the points, and they are in this, parabolic shape, for example, with some noise, of course, and you try to fit a linear line, it's not going to detect the pattern in the data, right? So you'll say, oh, the best way to fit this is maybe this horizontal line. Obviously, that has nothing to do with how the data is laid out. You're much better off if you could somehow do a non-linear analysis, and you can extract that quadratic shape, right? So a quadratic is an example of a non-linear relationship. We can do similar things in graphs. So what this, and as I said, we'll see examples of this later. What you can do is you can take a graph, and remember, graph is it's an object without any coordinates. It's not an x, y, z space, is it? I mean, it's just some pairwise relationship, right? So two objects are connected, but what are the coordinates? What is the x-axis? What is the y-axis? What is the z-axis? Or the higher order, axis? There is none. Graph is just a bunch of pairwise relationships, and it's just a matrix. Right? It's just a bunch of pairwise relationships. But what happens is that once you think of it as a kernel matrix, what you can do is you can embed. So this is sort of conceptually you have to think now. You can take a graph, okay, and you can embed this in this new space, okay, in this new coordinate space. So essentially, okay, let me give you an idea of what I'm talking about, because without a figure, it might be hard to sort of gauge what I'm referring to. And this, again, it opens up a whole bunch of powerful analysis that we can do on graph structures. So you have a graph, okay? So this is a graph. It's a simple one with the two triangles connected to each other. Now, if I want to analyze this, okay, I can do, there are many things you can do with it. You can do degree distribution, and I'll talk about more things. But one of the things that you probably want to say is that, okay, what if I can take this graph and I can map it to a coordinate frame? That is, go from here via some, we call this a mapping function, to a x, y, z coordinates. Okay, so the idea there would be, so let's say node number 1, node number 2, node number 3, 4, 5, and 6. Now, depending on how I define my similarity and so on, but maybe, for example, if my goal is to do clustering, I might say, okay, here's one cluster, right? It's a triangle, very tight. Of course, it's a complete subgraph. Here's another cluster. And how can I extract those clusters? So one idea would be, if I can take the graph and I can map it to a XYZ frame, for example, XYZ coordinate space. And what if it were the case that 1 lands up here, 2 lands up here, and 3 lands up here, and maybe 4 lands up here, 5 lands up here, 6 lands up here, right? So what and this is ideal, ideally if you're trying to do clustering, this is what you want. You want things that are highly similar to each other to be grouped close by, right? And then the two groups should be far apart. So that would of course depend on how many paths there are and those kinds of things. So how you measure similarity, it could be shortest path, it could be something else. But this is what you really want. And then, so this is actually called an embedding. So this is a graph G. Embedding of G in an R, in this case R3. R3 is a real space in 3 dimensions, X, Y, Z. Of course, typically you will not know what the value should be. It could be 4-dimensional, it could be a 100-dimensional space. Okay, it can be really high-dimensional, space. But conceptually, that's what you're doing. You're going from a graph, which is a dimensionless, coordinate-free, just a bunch of relationships, to a coordinate space. And then I can do my classic, data mining algorithm. I can apply we can talk about this later, like a k-means clustering on this. And it would basically say, okay, here's one cluster, here's one cluster. So I can detect, okay, clusters. I can do these kinds of things if I can do this mapping. So this kind of mapping is, as I said, very closely tied to the adjacency matrix. to the kernel matrix actually. So the adjacency matrix based on some notion of similarity between the nodes. So these are things we'll talk about in subsequent lectures. I'm not going to spend more time on this, but this really opens up a whole bunch of powerful tools that we have. Essentially, everything that we know in data mining and machine learning, we can apply. Because once you map it to that space, right, it just becomes a bunch of points in a real coordinate space, and we can do lots and lots of powerful techniques. Things like support vector machines you may have heard of. We can do neural networks, deep neural networks. Deep learning is now one of the cutting edge sort of in terms of the computational performance. I'm sorry, the classification performance. So one can apply many other So in other words, I guess the point I'm trying to say is that yes, graphs are a distinct object, and we can study graphs like graphs, talk about paths and things. But graphs can also be embedded in a real space, and now suddenly you can think of graphs from the point of view of a graph structure or just from a bunch of points, with similarity, and do a whole bunch of analysis from both the angles. So this really opens up lots of avenues for mining this kind of data. All right, so that's that. Okay, so let's talk about other. Okay, these are our first sort of encounter with some. So now, what can we learn about these structures? So I'm going to define some again basic concepts that will help us understand what's happening. So we talked about degree. Maybe we didn't really talk about degree so much, but what is the degree of a graph? Okay, normally the degree is the number of neighbors, right? How many edges that are incident on a given node. But if your graph is weighted, right? So for example, here's a graph. I mean, a very small fragment, let's say. So here's a node, and it's connected to 4 other nodes. So let's say this is vertex V. So we can say that the degree of V is 4, right? So it has 4 neighbors. Okay, but what if the edges had weight on it, right? So for example, this had weight 1, this had weight 2, this had weight 3, this had weight 1. So we can actually use the weight as part of the notion of a degree. So the more the weights that are incident on you, the higher your degree will be. So in this case, actually we'll say is simply the summation of all the things, right? So the weighted degree is going to be 3 plus 2 plus 1 plus 1. So 7. Okay, so one can talk about the degree of V is 7, with weights of course. So we can use the notion of weight. So obviously things that have very high connections with someone else, they'll get bigger degree. So now the degree is dependent not only on the number of neighbors, it's also dependent on the weights of those edges, right? So that's a very important sort of generalization. So now we can talk about weighted graphs in the same way as unweighted graphs. Okay, but here's our first real statistic. Okay, the mean, the average degree, right? So any graph that I give you, your first question should be, what is the average degree, right? Because we want to know what is the average height, what is the average this, what is the, for any given set of numbers, you want to know what the mean is, right? And then of course you may want to know what the deviation is. So not only do you want to know the central value, but how widely spread it is, how big is the spread. So the mean degree is very easy. So if I have the degrees of every vertex, whether it's unweighted or weighted, I can just add them up and divide by n, right? So it's the average degree. All right, so that's an easy thing to compute. But here's here's again something very interesting we can. So even this simple statistic, it turns out that even the simple statistic, it is, when you talk about random graphs versus again real world networks. Now, why do we compute the mean? Like I said, we compute the mean because we want to know what a typical person, what a typical node looks like, right? In a network. So I could say if I'm looking at a social network, I'll say, okay, the average connectivity is 10 people. Okay, so any person is connected to 10 other friends, for example. So, okay, so you say, I computed this number, it's 10. But the problem is this, that in a real world network, you have, as I mentioned before, it's a power law, right? Which we'll see again shortly, but it's a power law. So what that means is that there are lots and lots of people with very small degree, maybe degree 1, degree 2, okay? And then, so you've got maybe 100,000 of these people with degree 1, degree 2. Okay, but here's one node. Okay, let's pick a notorious example. You may have heard of Justin Bieber, right? Notorious character. But this guy has 1 million, connections. Okay, so if I now compute the average, what's going to happen? It's extremely skewed, right? So you have very small numbers and you've got an extremely large number. So this one person has 100 million followers and you've got 100 million people with just degree 1 or 2. But what is the average degree, right? It's somewhere in between. And this average degree is meaningless. Right? It does not characterize your network at all, right? So this is the problem that we face in real world graphs, that normally under normal conditions the mean means something, and when I say this is the mean, you get some valuable information back from that. But in a real world social network, it's actually meaningless to talk about the mean value because it is not representative of anyone. Okay, because of this extreme. There are ways of getting around it. You might say take the hub nodes and throw them away, right? And then compute the trimmed mean. So you can do those kinds of processes, and that might be more representative of what's really happening in your network. So anyway, so as I said, even in a small, and then okay, what about the variance, right? So the variance would be, it's not here, but the variance would be defined as follows, right? So if I look at sigma d squared, the sigma squared is the variance, right? So it's basically sum of di minus mu d squared by n, right? So that would be, again, the deviation. So now you want to know how much do you deviate from the mean, right? And normally, if you think of the way many things happen in nature, you have the normal distribution, right? You've heard of the things happen in a bell shape. Here's your mean value, and you have a standard deviation sigma. Actually, let's not put a d there. And everyone has heard of Six Sigma, right? So in business they talk about Six Sigma as it's like a quality control thing, right? So what does Six Sigma mean actually? Six Sigma basically says you are plus or minus 3 standard deviations from the mean. So you can be 3 deviations up or 3 deviations down. So that's 1 deviation, 2 deviations, 3 deviations, right? So that's actually 3 sigma. And then on this side would be minus 3 sigma, right? And in a normal distribution, this 6 sigma will encapsulate 99.999% of the population, because that's what the normal distribution is. It's actually very, very squished, right? All the probability is within the 3 sigma. And there are very few things in the tail. So we call these the tail ends. So if you look at the tail, the normal distribution never obviously goes to 0. But it goes extremely, close to 0. Right? So the tail extends infinitely on both sides. So this is called the tail region. So in a normal distribution, this is like what we would like to see. But unfortunately, again, in a real world network, like a social network, you will not see that. If you look at the 6 sigma, you will not find all the nodes within that, there'll be long, long tails. Again, because of the zip tree and the power laws, you find there's a probability of having very high degree nodes also. So the point is that the deviation can be extremely large. Again, you've got one node with 1 million degree, some nodes with very small degree. So the variance by definition is extremely high. So those are the, so again, these things are good to measure, but one has to be understanding, what are we really trying to find out based on that. So we'll come back to this and look at this more when we talk about, models for real world networks and how they come about. Okay, so degree is one thing one can study. We can do the mean, the variance. So this is the variance. Okay, what else can we do, right? So we can obviously do path length. So I said the shortest distance between two nodes is defined as d, vi, vj. So that's the number of hops, the shortest number of hops it takes you to go from I to j. And so this is for an undirected network. So there are n choose 2 pairs of vertices vi, vj, and you go for every I, you look at all the j that are greater than I, because it's a symmetric graph, right? And so this would be an average path length. So how many, on average, how long does it take you to get from one end to the other end? And you can also do the variance if you want. Now this average path length again is very interesting. Real world networks, the average path length, it's called, you've probably heard of the small world phenomenon, right? Or if you look at so how many hops does it take? So if I pick any two people in this room actually, and I say, let's find out, right, what connects any two of us, and we say, okay, so, and you can use all kinds of facts, right? So you are from this place or that, so we can define what the rules of the game are. But it turns out that normally, in any real world networks, there are only a few number of hops, maybe 6 or 7, and you can pretty much reach anyone, right, from one endpoint to the other. So there was a very famous experiment actually done by the social scientist Stanley Milgram from Stanford, right, in the 70s or something. So they had to route letters from one end of the US to the other end. Okay, so from, Stanford is in San Francisco, okay, in the West Coast in California. And the people had to send a letter to people in Boston, right? Boston is on the East Coast. So from one end of the country to the other end of the country. And what were the rules? The rules were that you could not obviously send it directly to the person. What you could do is you could put a note, okay? And the note was simply, the final address was probably given, but the idea was that you just send the letter to some random person, and you just say, you forward it to someone you know. But the idea is to keep the chain. It's like a chain mail letter, right? We get them in the email all the time. And you just add your name to the bottom, and you forward it to the next person. And you keep on doing this. And this whole chain would be a success if you end up reaching the right person. Okay, so in Boston, so if I want to send them to my relatives in Boston, whatever, how many hops? So then you can count how many hops it took you to get there. Now, of course, in any real world experiment like this, let's say, I don't know the exact fraction, but let's say 80 to 90% of the letters never make it, right? Because, I get a letter, it's just like a random, chain email. I just hit the delete button. But sometimes I may think, oh, it's a good content, I'll send it to my friend, right? So you forward it on. So let's say 10-20% success rate. But these letters actually reached Boston. Let's say 20% of them reached Boston. And then they looked at how many hops. And it just turned out to be 5 or 6 hops. So this sort of notion of, it's a very, very small world phenomenon. So one can look at these average path lengths, and basically we know now that, many real world networks are these small world. So this is one of the key sort of features, okay, of a real world network. And then the question would be, a natural question that we should be asking is, all right, why is it that real networks are small world? Why is it they're not a very, very long, a number of hops to get from one end to the other? And one can even show that actually these networks become smaller and smaller in time. So if you actually study the evolution of the network in time, they become denser, means more and more connections come about, and also the path length actually shrinks. Because in some sense it's counterintuitive, right? If I'm adding more nodes, normally you would expect the distance to increase, right? More nodes are being added, that means the number of hops is increasing. But it turns out that actually it shrinks. So this is called densification law. We can talk about other laws of real world networks, but it's called densification in time, that the network becomes denser and the average path length actually shrinks if you look at the temporal evolution of these networks. Alright, so this is just a more graph. And this was just some example of, degree distribution and so on, which I'm going to skip. Alright, a few more concepts, and then I think after that we'll take a break for some time. So let's just finish this part, because this is closely related to the notion of, like what other metrics can be defined. So we already saw the path length, right? So the average path length is look at the shortest path between any two nodes and then compute the average for those. We can define something called the eccentricity. Okay? The eccentricity of a node is actually the maximum distance. So for a given node, I can compute how eccentric you are, right? So basically how strange you are in a network sense. So if you are very far away from the rest of the network, then you are very, very strange, right? You're sort of far removed. And if it were a similarity, this would probably make more, it would make real sense that someone is actually highly dissimilar from the rest of the network. That means you're probably really strange, so you're more eccentric. Anyway, so that's the maximum. So for any given node, I can compute what is the maximum distance to someone else. And then I can actually define for the whole graph. So, I can define a notion of a radius. It's almost like it's a circle of some kind, right? So one can say, what is the radius? The radius of the graph now is the minimum eccentricity. Okay, so a node that is sort of not very far from everyone else. So look at all the nodes. Some nodes are going to be far, some are going to be sort of in the middle of the network. So you define the radius sort of based on those middle nodes, right? So think of a network that's sort of radiating out. So maybe a node is here, and you get a radial expansion from that. Right, so in this network, right, obviously this node here will have the shortest sort of path to everyone else. So the minimum would be probably with respect to that vertex. So that will define the radius. So among all, so like if you pick this one, the distance is very large. If you pick that one, it's sort of equally close to everyone else. So this would be your, it will define the radius of the graph. So the radius of, in other words, and there can obviously be more than one. Maybe there's another node here. So maybe these two are the middle nodes, right? The center node, if you will. So again, we sort of just measure, and the minimum value is taken to be the radius of the network, and then as you can imagine, the maximum value is the diameter. So one can talk about the diameter and the radius. So the radius is the minimum eccentricity among all the nodes, and the diameter is the maximum eccentricity. So it's actually, simply put, it's really the maximum distance between any two pairs. But I can think of it in terms of the eccentricity of vertices. So we pick. So radius is the min, diameter is the max. The average path length was the average, So these are just, basic. Essentially what we're doing is we're computing basic statistics on the path lengths. Alright, yeah, and this is important. So the notion of effective diameter. So, when people looked at real world networks, and I talked about this whole great thing about, we live in a small world and so on and so forth. But actually things are not exactly, real life is never perfect, right? So in fact, it turns out that there are these long paths sometimes. Okay, so think of a network like this. Think of a network where, majority of the people are here. Okay, they are all, tightly connected to each other in some way, right? But then somehow, I don't know, for some reason, you have this long, tail here. Now, let's say 95% of the nodes are here, and let's say 5% of the nodes are here. Now, if you look at this, and let's assume this is a real world network, and you compute the average path length and the diameter and the radius, again, what you're doing is you're skewing the whole thing, right? Just because they have this one thing that's hanging off on one end, and maybe several instances of this, you get a very large value. Whereas 95% of the nodes are really very tightly connected. Okay? So if you look at real world networks, you do see these kinds of structures. And so it's kind of like, if I really want to compute the radius and the diameter and the average path length, it will be actually long. Just because of this one, or a few of these tails. So what we want to do is normally, we want to ignore these ways. So we say, actually just ignore this and compute the averages, the eccentricities for the remaining. You could be very strict. You could say, I want 99% of the node. You pick a threshold, okay, whatever makes you happy, 90%, 95%, 99%. But the effective diameter is actually for that fraction. We say, this is the radius, okay, or the diameter for the 90% of the nodes. And this is what is really small in a real world network. So there's something to keep in mind that, yes, there are obviously these, real life never follows all rules exactly. So there's noise. So we talk about effective diameter. So effective diameter is simply take this definition and compute the max, but then throw away the 5%, the highest 5% of the values, throw them away. Whatever remains, the maximum of that is the diameter. Okay? So that covers 90 or 95% of the nodes in the network. So we'll stop in 5 minutes. So this is the last thing we'll do before the break. And this is pretty much the last thing before we go on to the other sort of part of the. So this is sort of just setting up the definition, what we're going to talk about. This is an extremely important notion when you want to analyze, real-world networks, especially social networks. The notion of a clustering coefficient. Now the background to this is, let me ask a very simple question. So, I am a node, I have this friend, I have that friend. Okay. The question that we want to ask is, how likely are these two people to be friends with each other? Okay. This is called closing the triangle. So, or closing the V, if you will. So, the degree to which we can, close. So, in a social network, it's very likely actually that two of your friends will also be friends of each other. Right? Because by chance or over time, you have one friend, you have another friend, you're obviously going to introduce them to each other at some point in time. So that loop will close. They will probably, if they hit it off, they'll become friends of each other. So you tend to close these loops very quickly. Okay? And that is a measure of sort of your connectivity, your social connectivity. Okay, so your friends of your friends, right? How are they friends among themselves? So that's what this clustering coefficient actually tends to measure. That is how much of a local clustering effect there is, how much of this closing of the loop there is. And so how do we define it? Okay, so we define it as follows. For any given node, okay, so this is like a node-centric idea, so that we can compute this for each node in the network. You first look at this thing called GI, okay, I'm going to define that. So you look at the number of nodes, basically it's, in simple words, it is the number of these closed edges among my friends. Okay? So how many of them are friends of each other, basically? And what is the maximum number of pairwise relationships that could be there? So this ratio gives you an indication of your. So in other words, if I had 10 friends and all of them were mutually friends of each other, my clustering coefficient would be 1. Okay, because all of them are friends of each other. So there are 10 choose 2 possible neighbors, and they could have connected, and they're all connected to each other. Or the other extreme is I have 10 friends, and none of them talk to each other, right? They have no connections, so that would be clustering coefficient of 0. So it's basically a star shape. So this would be an example of a star shape. Here's a node. This node has 4 neighbors, and none of them are friends of each other, for example. Right? So clustering coefficient is 0. So for this node, V, I will say the clustering coefficient is basically 0. Because there are no edges present, like this edge is absent, that edge is absent, and all those edges are not existing in the network, right? So, but how many edges could have been there? Well, if there are 4 neighbors, there are 4 choose 2, right? So there are basically 6. So there could have been 6 possible, there could have been 6 possible edges. None of them is present, so the clustering coefficient is 0. Okay, so that's not a very interesting node as such, because none of the friends are talking to each other. On the other hand, I could have another node here, and this could also have 4 neighbors. But let's say now, this node talks to that node, this node also talks to that node, this node talks to that node. So let's say there are 3, right? So out of all the possible neighbors, which are, there are 4 neighbors, so there are again 6 choices, but only 3 of them are present, right? The 3 red edges. So the clustering coefficient for x, so C of x will be 3 out of 6 or 50%. So we can use this notion again, like I said, to see how well connected you are. And this has, this has applications beyond just friendship, right? This can be applied to logistics. If you're talking about disaster planning, the floods in Madras, in Chennai, right? So you want to do logistics supplies. So it's a question of saying that if this hub fails, right? So for example, if this hub fails, what's going to happen? Right? All those 4 people are stranded, right? They're not going to get any help. Whereas if this one fails, there are many other connections still there. That means there are alternate routes. And so these kind of notions are extremely important when you talk about resilience, to disruptive affairs, natural disasters, other disasters, logistical planning, aid, relief. So these are, again, they go back to, so these are the fundamental questions we really want to ask when you talk about networks, right? Who's important? What are the failure points, right? What are the, how long does it take you to get from one end to the other? How are people connected? So essentially, these are all notions that are getting us to understand those things. So I'm going to take a break here, and then we'll continue from here.
We can take 10 minutes break. Maximum 10 minutes.